Let's see. Hey, there he is. He made it. All right, everyone is here. Very good, very good. Then let us begin. Good morning, everybody. Today we get to talk about some super special, awesome stuff. We get to deal with 3D shapes, which in my opinion are just the coolest. Like, that's the best part about geometry, is we get to build things and manipulate them, okay? But we're still only on the preview stage, so we're just going to run through some basic definitions here, do some quick sketches of things, start to flex that visual spatial reasoning part of your brain. We'll hit a little bit more of that when we talk about calculating volume of things for the SAT questions later in this quarter. And then next semester, I've blocked out the whole fourth quarter all about 3D geometry, okay? So it's really going to come at you. You got to get your special glasses for that. Just kidding. Anyways, if bread is the first necessity of life, recreation is a close second. I heartily agree. That's why we'll be playing some more riddle games on Friday. So without further ado, yesterday we ran through the quadrilaterals and circles. So here are my final answers for that section. Go ahead and take yours out to check how you did. First page should be pretty straightforward. 1, 2, 3, 5. We had basically done with just sans the lettering. 6 was a little bit more. They specified a perimeter, so you should have said, hey, one of these sides has to be A and another side should be 2B because I have A, and then the other side will be exactly the same, so a total of 2A, and then 2B plus 2B gives you 4B when you add them all up. Doesn't matter which side you labeled, so long as one of them is A and one of them that is not the opposite side was 2B. Number 4, though, was tricksy. And I may have led you astray with my original drawing because I only had this bit of a trapezoid. Said, hey, it's got a perpendicular there. That should be part of the trapezoid. But if you look closely at which letters are required, and you notice P, E, and A are collinear, the only way to make that happen is, I would say, put them on a line first. Start one step at a time. P, E, and A. Make a line with all of those there. I know A and P are part of my trapezoid vertices. Those have to be the endpoints. So there's got to be an E somewhere in the middle. And then from that line, wait a minute, RE is the perpendicular part. R is not already on this line. So there must be another segment RE that is perpendicular here. Right? This is why we started with that logical reasoning, so you can think through these kinds of things and deduce. This is the way it has to be, because there's no other way to make this work based on the information I am told. All right? So you go with more of the classic trapezoid shape with both sides being at an angle here, and we'll also draw in this, what would be referred to as an altitude, an extra line in the middle perpendicular to a base. All right, zoom out, there we go. Now, the next set, naming the figures from the grid. There's actually several options here for some of these. The square, however, is not one of them. There's only the one square right here. You must have these 4 letters, although the order here could be, you could have D, then F, C, A. It doesn't matter where you start or what direction you go, but they should all be in that order. Please don't jump like D, C, F, A. Make it diagonal or anything. And then the parallelogram, lots of things in here are parallelograms, right? The rhombus is a parallelogram. You could repeat this one in your answer for the parallelogram. A square is a parallelogram. You could put that in there. Or any of these rectangles. I chose to go with the little one up top. You could go with the whole thing here is a big rectangle, thus a parallelogram. Lots of options there. As noted, the rhombus there with point J, using this guy here. What a lot of people might call a diamond shape is actually a rhombus. And then HFBD, this slightly shortened one, is the only kite on the list that is purely a kite. You could also still list the rhombus. A rhombus is technically also a kite. Remember our definition, kite has to have two adjacent congruent sides. It doesn't say that these two can't be congruent to each other. So since the rhombus says, hey, these two are adjacent and congruent, these two are adjacent and congruent, rhombus could be a kite as well. It's a kite and a parallelogram at the same time. A lot of overlap with these guys. All right, any questions on the first page? No. Then on to the second, the cycles. Measure of arc QR, we already knew that one, that was 48 degrees. Measure of arc PR, that would be going the other section of that half a circle, so I would say 180 minus 48 to find 132 degrees. Measure of arc PQR. So now we got triple letters. So that means don't go from P straight to R in the shortest route possible. You must go around from P through Q, then to R. So talking about that larger one. So you could take 360 minus the 132, or you could take 180 plus 48. Either way, we get you 228. And then arc QPR, Q to P to R is almost the whole circle except for that original slice. So 360 minus 48 to get 312. Five and six sketches, I finished those in class. There was nothing else to add to those. All right, so you should have something similar on your page. And then for number 7, these 2 points given are a distance 5 apart. You can find that by just subtracting it from -2 and 3. And then add that radius on to the y value to get 3, 7. Subtract from the y value to get 3, -3. And add to the x value to get 8, 2. So there's your 3 points on the circle. Any questions from that page? No? All right, then let us begin with our three-dimensional shapes. And I've set up a quick grid, what am I looking for, chart here. And I would ask you to recreate something similar in your notes, if you haven't already, because there's some very simple ways to define these shapes. All right, we've got the 4 basic three-dimensional shapes: prism, pyramid, cylinder, and cone. We'll see those a lot. All right, and I have a selection of some here on my desk. I'll hold those up for the camera for you to see. It's not as great as if you were to actually be here in physics, because you only see the 2-dimensional, image of my 3-dimensional object. Those of you in class, right, you get to multiple angles at once from this thing, right? So here is the cone. Here is my cylinder. Here are a couple of prisms. This one is a pentagonal prism. Guess why? Here is a triangular prism. And then here's a set of pyramids. We've got a square pyramid and a triangular pyramid here. Okay. Most of these you could probably recognize right away. I bet a lot of you could sort them into pyramids here, prisms over there, pretty easily. There's some very defining characteristics, okay? And they have to do with the number and type of bases and the number and type of sides, okay? Which the side idea kind of breaks down when we get to the round ones, but bear with me, okay? So, first off, what defines a prism? A prism must have 2 congruent polygon bases. Okay? It is only a prism if you have two congruent polygon bases. And even better, they are going to be parallel to each other. Just like you can have lines that are parallel, that are the same distance apart and never ever meet, you can have shapes existing in three-dimensional space. Nice flat shapes that are parallel to each other and never ever meet. Right? So take the triangular pyramid, for example. Here's a triangle on this side. Here's a triangle on this side. Those two triangles are parallel to each other. Right? I can rotate this and you can see they're not slanted inwards towards each other, right, in any way. And each triangle is exactly the same size and shape as the other one. Okay? Same with the pentagonal one here. Right? Pentagon on both sides, exactly the same. If you make one like smaller, then you would cause the whole thing to start to form like a funnel shape, and then it wouldn't be a prism anymore. So they have to be the same size. They have to be the same shape, otherwise you get this some funky twisted combination of thing. We'll talk more about that next semester, the weird shapes you can make when you start to break the rules. It's really fun stuff. We've got to set the rules first, okay? So a prism has two polygons. Those two polygons are connected by the other, I'll call them sides, right? If these are the bases, the rest of them can be sides. And in a prism, no matter what you use for the base, you're always going to connect them with a whole bunch of rectangles. Okay? So the sides are all rectangles. See that? Some form of rectangle there. Now, I'm going to show you how to come up with a quick sketch for these, but I need you to tell me what shape you would like me to draw. So I'm posting a quick poll here in the Zoom chat. Follow that, vote on your favorite polygon I will use as a base. Triangle, square, pentagon, or hexagon. Which one would you like to see me sketch up here? Three votes in. So far, square is winning. All right, if you don't want to see a simple square prism, vote now. All right, that's 4 more votes for square. Okay, square is going to take it. All right, but the same principle applies. So I'm going to color code. Let's see, actually, why don't we do this? We'll keep bases in blue, and we'll make sides into, I don't have a color that starts with S, so we'll just go with red. All right, so start with your base. So we want a square, so draw yourself a quick square there. And then, up and to the right, repeat that. Draw the exact same square. Somewhere over, and the farther away it is, the longer your prism will be. Let's make that a straight line. Okay? 2 squares. Now, if this was a triangular prism, right, or a pentagonal prism, you would draw your triangles or pentagons appropriately. And now, it's as simple as connecting all the vertices. We'll draw one line there. We'll draw another line there. A line there. And then a line through there. Boom, square-based prism. All right? That's it. That's all it takes. And if you want to get real fancy with it, then we would actually not draw that side because we couldn't see it. If you wanted to think of this as a three-dimensional object, a solid piece of what you could see and what you could not. If it's solid, then you wouldn't have that line, you wouldn't have that line, and you wouldn't have that line. Look, it looks like a stick of butter, doesn't it? Just need to, color that in yellow, put it on toast. Right? There we go. Prism. But for now, we'll go ahead and keep all the sides. You could also, if you prefer, make those into dashed lines. Go with a partial eraser here. To indicate that they are behind and not easily visible. Right? So those would be the back lines, and that way you don't have this awkward effect of like, wait, is it a box coming out of the page or is it a hole going into the page? You got that visual paradox there. All right, so there's your prism. Pyramid, very similar. Pyramid has one polygon base. So a prism requires two matching polygons as bases. A prism has a single polygon as its base, and its sides are all triangles. And they meet at the vertex. Now, I say the vertex. Take a look at this pyramid right here. We've got a square base. All right? So that's our polygon that's a base. And then every other face of this thing, here's a triangle, here's a triangle, here's another triangle, right? We've got a whole bunch of triangles, all meet up at this single point. Now, generally speaking, when we're talking about three-dimensional shapes, the flat pieces are called faces. The lines there are called edges, and where any of the lines meet, they call that a vertex. Just like we have the vertex of the polygon, still the corners. Okay? But a pyramid is special because while all of these pointy bits are vertexes, there is one here called the vertex, and it gets big fancy name. It's the vertex. This is just a vertex. This is the vertex of all vertexes, where all those triangles meet. It's the pointiest bit of the pyramid, the tippy top. Okay? The now missing gold cap that was on the great one in Egypt, right? That's the vertex, okay? And it plays some very special roles in our calculations later on. All right. Drawing a pyramid is also rather simple, but we're going to have to deal with a little bit of perspective here. So I'm going to stick with the square, just so it matches my prism, except we're not going to draw a square face on. We're going to draw a square as if you laid it down and you're looking at it down from the desk. Okay? So like, lean back and look at your keyboard right now. It is not a perfect rectangle. Okay? Visually, the way it fills your visual field, it more resembles possibly a parallelogram, but maybe even a bit like a trapezoid, because it's actually the back edge is smaller than the front, perspective, right? So we're going to draw more of a rhombus-looking shape. We'll go about that big, that big, that big, and there. So even though it's a square-based pyramid, we're actually going to draw more of a rhombus because you want it slantwise. And then pick a point way up above your base. You can put it up here if you want a short pyramid. You can put it up there if you want a nice tall pyramid. And then quite literally connect that dot, and straight line, please. There we go. To all of the vertices of the shape you just drew. Okay? So if you wanted a hexagon-based pyramid, a hexagonal pyramid, or a pentagonal pyramid, you would draw some kind of slanted hexagon or pentagon down there, and then you connect all of them up, single line to the top. And once again, I think we need a little smaller of an eraser here. Yeah, that looks good. We can go back in and make these, oops, not there. Make these back ones into dashed lines to indicate those would not be seen from the front view. Okay? Now it gets a little bit more of that 3D effect with our V vertex on the top, the most important one. Questions so far? No? All right. It's like I'm teaching an art class all of a sudden. Right? How to draw three-dimensional shapes. All right, cylinders and cones. There is a very strong relationship between cylinders and prisms. A cylinder is really just a super special prism. It has all the same features, except instead of a polygon as its base, it uses a full circle for a base. Cone, likewise, very strongly related to a pyramid. It resembles one in many aspects, except instead of a polygon base, it uses, again, a circle. So these are the round versions of the same thing. So a cylinder has two circles, again, parallel circles, and its side, this is why I put that in quotes, because there's not individual sides here. It's all one wrapping around kind of face. But if you were to cut this guy open, tear it apart, and flatten it out, it would be one rectangle, right? You take the label off of a soup can and unroll it, and what do you get? You get a long, skinny rectangle, right? So it's still effectively a rectangular side. And that is what we will use when we get to the calculating surface area. We'll treat that as a rectangle. All right, now you could do the same thing as the prism. We could draw a circle, draw another circle, and then we just connect the top and the bottom. That doesn't look that good. It's kind of garbage in my opinion. So we're going to do one better. Where's the delete? There we go. We're going to use our slanted perspective style, just like with the pyramid, and we'll draw what turns out to be more of an ellipse. Just like that. And then above that, you'll draw the top of your cylinder, a matching ellipse. They should be pretty close to the same size. Line them up there. Might take some practice, all right? It's all in that wrist motion there, back and forth. And now we connect both sides with straight lines, just like that. You might find it easier in lining them up. Notice right, I kind of missed there. If you want to draw the sides up first, and then you can slowly draw in your ellipse like that. One time, make sure you hit those sides a little better. Okay? That's a little bit better of a cylinder. And then again, looking at this, you wouldn't see the back of the bottom one there, so we'd make that into our dashed line. There is our cylinder, looking like a soup can sitting there on the counter. So you can see the top of it pretty good. You can see the front and the front bottom edge, but not the back edge. Not too bad. All right, cones. Cone, I bet you could predict this one. One circle base. How about the side? Well, it's not a rectangle or a triangle anymore because it's round, so it's not a polygon shape, and we can't even unravel this to make a perfect rectangle either. You really end up with a sector of a circle. So I'm going to write that down, but it's not that useful. We'll have a better, more straightforward formula for getting the surface area on it. But if you were to unwrap the cone, you would find you've got your circular base there, and the other part has some curvature to it. Now, let's go in a little bit steeper, like that. Okay? So it's almost a large triangle, but you've got this bit here that is round. And so because that is round, this is actually a sector of a circle. Imagine, if you will, I was to continue this curve around. It's a pizza slice, all right? It's a really wide pizza slice. Luckily, we don't need that piece for drawing a cone. Similar to the cylinder, I would start with an ellipse as our base on the bottom. Just like the pyramid, pick your tippy-top vertex point, and then you just need two lines out to the left side and the right side of your circle. We can go back and erase a bit to make the back one dashed line. There you have it. Beautiful cone. Any questions so far? No? All right, then that should set you up for today's worksheet, where they ask you to draw a prism with a rectangular base. A square is a more special rectangle. Okay? So just generalize from there. A cylinder with base diameter greater than its height. So short, fat cylinder. Draw a can of tuna instead of a can of soup. Now the next thing I want to talk about is nets. This is really going to test your spatial reasoning skills. And if you look at this and you can interpret it immediately, congratulations, you have really good spatial reasoning skills already. Not everybody has that. Okay? What you're looking at here is I should be able to cut this out of a sheet of paper and fold it along the lines and tape them together to create one of these shapes. Right? Just like I was talking about with the cylinder. Right? You take the label off your soup can and unravel it, and you get a rectangle. Well, you then apply can opener, right? Cut out the top and cut out the bottom. Two circles and a rectangle. That's the net of a cylinder. It's how you would cut out a paper craft and fold it back up. Right? If you want to see this in action, Google search nets of 3D shapes, nets of solids or whatever, and they've got lots of animations out there. I found some here that are really cool. Okay, check this out. Here I have 6 squares laid out, connected to each other, and I can slowly close them up and fold it in just to form a box. There's your net of a cube, right? And in fact, that's not the only net of a cube, because I could connect these in several different ways, right? I could rearrange this however I like, and we could still fold them up together and form a box. We can go like partway through and view this around in 3D, see? So if you've ever done any packing up, right, and you've had to put together the U-Haul boxes, right, and you fold, it comes in perfectly flat, and then you got to fold it around together and tape it up to form an actual box. That's what you're doing here. That's a net. That's really cool. Here's a rectangular prism one. All right, so it starts out perfectly flat, and then we fold it up, to form a full 3D box, right? And you can do that with other things. Here's a hexagonal prism. You can unfold that guy. So there you see the two hexagonal bases, 1, 2, 3, 4, 5, 6 rectangle sides all flattened out, all right? So that's what we're looking for with the nets. And I encourage you, use Google. All right, just search if you want an animated version. You can find some. See if we can get a nice pyramid one. Right, ooh, look at this guy going. Oh, I like that. We'll get to that shape later in the year, right? Lots of cool stuff on the internet for you, right? Google some pictures there. Look at that guy going. Octahedrons, okay? So that's going to be nets. It takes some practice with them. Right? But there should be some interpretation based on, what I've said. Here, it's going to be one of these four options. Do you have two congruent polygons, or do you only have one? That's going to narrow it down. Are there any circles involved? Right? That's going to narrow it down. Okay? So it should be relatively straightforward to identify what type of shape it has to be able to form, even if you can't quite see it. All right, then the next couple of tasks, I don't have good general tips for you. You're going to have to work through these yourself. You can look this slices thing. I think you can also search up some animations on that. Right, but try to do that yourself. Picture this object in your brain and imagine it's completely solid. And we're going to chop it in half. Okay? And we're going to take that half and look at it, like use it as a stamp. Okay? So imagine your oranges in the morning for breakfast. You cut it in half. It starts out as a perfectly round sphere. And then you cut it in half, and now you look at that face, that flat side you've created now as a perfect circle. Right? What do you end up with if you slice a cylinder this way? How about a cone? What kind of shape do you get? Okay? Try to work that through your head. And then 7 and 8. Similarly, visualize this object in your mind. Pick it up and manipulate it. Look around it. Okay? This is a rectangular prism made up of a bunch of little cubes. It's almost but not quite a Rubik's Cube. So if you have a Rubik's Cube at home, test this out and be like, okay, what if it was the Rubik's Cube and they asked me this question? If you look at it such that you can only see exactly 3 sides. Let me get an actual cube here. All right? If you hold this in such a way that you can only see 3 of the sides, right? 1, 2, 3. There's 3 other sides, the ones that I'm holding on to, that you can't see, right? That's how we take advantage of that when we try to draw a cube, right? So how many of the little cubes are hiding back here that you can't see at all? Careful, the ones on the edge, right? These ones along the edge there, you can see part of that. You can see one face of that cube, so don't count the square back here because it's attached to that little cube up there, right? So work through that. Okay? And then number 8 is a little bit interesting. You're going to have to transfer some of these values, okay? If this is a 3-dimensional object, its height is consistent. It doesn't matter if you measure on the left side or if you measure on the right side. The height of the thing is still the same, right? So when it says right here that it's 4 tall right there, it's also 4 tall over here. It's also 4 tall in the back that we can't see. It's also 4 tall in the front, right? So any combination of heights stacked together that go from the bottom of the shape to the top of the shape has to be a total of 4. So use that kind of information to transfer and work out, okay, this plus this has to be that one, and subtract and add to find x and y right there. Okay? And you will have to use all of the numbers there. There's no extra information. That's the final hint I'm going to give you on that. Any questions here? This is it, just this one section today. Because I know for some people, the jump to 3D is going to be a struggle in your mind. But it is a skill. It can be learned, but it has to be practiced. No questions? All right, then I leave you the rest of the period to work. Which is, what we got, 10 minutes? Yeah.